Every day, billions of products pass through a machine so ordinary that most people never notice it. A bottle of water, a carton of milk, a smartphone. Each one glides across a small window. A red flash appears. A single beep is heard. And almost instantly the correct name and price appear on the screen. It all happens so quickly that we rarely stop to ask a simple question. What actually happened inside that machine during that tiny fraction of a second? At first, the answer seems obvious. The scanner looks at the barcode, reads the numbers, and identifies the product. That's what most of us have believed for years. But almost every part of that explanation is wrong. The scanner never sees the product the way your eyes do. It doesn't recognize a bottle, phone, or a box of cereal. It doesn't even read the printed numbers beneath the barcode. The only thing it truly detects is light. So let's rewind everything. The product disappears from the checkout screen. The price vanishes. The database returns only a number. Digital signals become electrical waves again. The electronics fall silent. The laser stops. The mirrors freeze. Until finally, the scanner becomes nothing more than an empty shell waiting for its very first beam of light. Now imagine we have to build this entire machine from scratch. Our mission sounds almost impossible. Build a machine that can identify millions of different products in less than 1,000th of a second. But there's one rule. It is not allowed to use artificial intelligence. It cannot understand colors. It cannot recognize shapes. It cannot even know what product is sitting in front of it. The only thing this machine is allowed to measure is a beam of reflected light. So where do engineers even begin? The first challenge isn't recognizing a barcode. It's finding the fastest possible way to collect information from it. The obvious solution would be a camera. Cameras work perfectly for phones, robots, and self-driving cars. They capture everything they see. But that's exactly the problem. A camera captures far more information than a barcode scanner actually needs. It wastes time collecting details that have absolutely no value. Engineers realized they didn't need to see the entire barcode at all. They only needed a single line passing across it. Imagine drawing one perfectly straight line through every black bar and every white space. If that line is measured accurately enough, it already contains all the information needed to reconstruct the code. That simple decision completely changed how barcode scanners would be engineered for the next several decades. Once engineers decided to read only a single line instead of an entire image, a new problem immediately appeared. That line had to be incredibly thin, perfectly stable, and identical every single time the scanner was used. An ordinary light bulb couldn't do it. Even an LED spreads light in many different directions. The machine needed something far more precise. It needed a laser. Inside the scanner sits a tiny component called the red laser diode module. At first glance, it looks surprisingly unimportant. It's smaller than your fingertip and costs only a fraction of the entire machine. Yet every measurement that follows depends completely on this single device. If its beam becomes unstable, even by the smallest amount, every calculation that comes afterward will also become unreliable. Unlike ordinary light sources, a laser produces a beam that stays tightly focused over a long distance. The light travels in nearly the same direction and at nearly the same wavelength, creating an optical reference that the rest of the scanner can trust. For the first time, our machine has exactly what it needs: a stable beam of light. But surprisingly, it still can't read a barcode. A stationary laser can only illuminate a single point. A barcode isn't a single point. It's a long sequence of carefully spaced black bars and white gaps. Shining the beam at one location tells us almost nothing. To understand the entire barcode, the beam must travel smoothly from one side to the other. That creates our next engineering challenge. How do we move light with incredible precision? One obvious solution would be to move the entire scanner, but that would make every scan slower, heavier, and far less reliable. Another option would be asking people to slide every product at exactly the right speed and angle. Anyone who struggled to scan an item knows how unrealistic that idea is. Engineers needed something much smarter. Instead of moving the machine, they decided to move only the beam. The answer is hidden inside the high-speed scan mirror assembly. Rather than bending the laser itself, The scanner reflects the beam from a tiny mirror that oscillates hundreds of times every second. A movement so small, it almost invisible suddenly redirects the beam across the entire barcode. To us, it looks like a single red line. Inside the scanner, that beam is racing back and forth with extraordinary speed. Large supermarket scanners push this idea even further. Instead of relying on one moving mirror, they use a multi-line optical mirror array that splits the laser into dozens of scanning paths. Each path crosses the barcode from a different angle. That's why you can twist, rotate, or even flip a product, and the scanner still succeeds almost instantly. It isn't guessing. It's dramatically increasing the chance that one scan line captures the complete code. At this point, the machine has finally solved its optical challenge. It can generate a stable laser, sweep that beam across the barcode, and collect the reflected light. It feels like the scanner should finally be able to identify the product. But here's the surprising truth. Nothing has been read yet. Light may carry information, but light itself is not data, and computers cannot process photons directly. Everything we've built so far belongs to the optical system. The laser generates light. The mirrors move it. The barcode reflects it. But none of those components actually understand what they're seeing. They simply control photons. The real challenge begins now. Every bit of information is still trapped inside light, and light cannot travel through electronic circuits. Somehow, that beam must become electricity. That single problem gives birth to the next critical component, the photodiode sensor module. If the laser is the scanner's light source, the photodiode is its eye. But unlike your eyes, it doesn't recognize shapes, colors, or printed bars. It doesn't even know what a barcode looks like. The only thing it measures is the number of photons arriving at its surface every fraction of a second. As the laser sweeps across the barcode, bright spaces reflect far more light than black bars. That means the number of incoming photons constantly rises and falls. To the photodiode, there are no products, no packaging, and no barcode. There are only changes in light intensity. The entire barcode has now been reduced to a rapidly changing stream of photons. Inside the photodiode, something remarkable happens. Every incoming photon carries a tiny amount of energy. When enough of those photons strike the semiconductor, they free electrons trapped inside the material. Those electrons begin to move, creating an electrical current. For the very first time, information that existed only as light has crossed into the world of electronics. It feels like we've finally created usable data, but once again, new engineering problem appears almost immediately. The electrical signal produced by the photodiode is incredibly weak. It's so small that electrical noise from nearby circuits could easily overwhelm it. Feeding that signal directly into a processor would be like trying to hear a whisper in the middle of a crowded stadium. Engineers solve this problem with the signal processing PCB. The first stage carefully amplifies the tiny electrical signal without changing the information it carries. Every reflection from the barcode becomes stronger and easier to measure. But amplification has its own danger. It doesn't only amplify the signal, it also amplifies unwanted electrical noise hiding inside the circuit. That's why the next stage immediately filters the signal, removing frequencies and disturbances that don't belong to the barcode. Only after amplification and filtering does the scanner finally hold a clean electrical waveform. It no longer looks like a beam of light. It has become a stable analog signal, ready for the next stage. But processors still can't understand analog voltages. Modern processors speak only one language: digital information. Ones and zeros. Continuous electrical waves mean nothing to them. The scanner now faces another impossible-looking challenge. How do you convert a constantly changing voltage into precise digital data without losing the timing information hidden inside it? The answer lies inside one of the most important circuits in the entire machine, the analog to digital converter, or ADC. Up to this point, we've solved every optical and electrical problem inside the scanner. We can generate light, move it across the barcode, convert reflected photons into electricity, clean the signal, and finally transform it into digital data. It feels like the machine should now know exactly what product it's looking at. But once again, that assumption is completely wrong. The digital data leaving the ADC still isn't a barcode. It's simply a stream of binary measurements describing changes in reflected light over time. Turning that stream into meaningful information is the responsibility of the barcode decoder processor. But the decoder isn't searching for product names. It isn't searching for brands. It isn't even searching for numbers. Instead, the decoder measures timing with extraordinary precision. It compares how long the signal stays high, how long it stays low, where the pattern begins, where it ends, and whether every bar and every space follows the international barcode standard. A barcode isn't recognized by its appearance. It's recognized by its geometry and timing. Before accepting any result, the decoder performs several verification steps. It checks the structure, validates the start and stop patterns, and calculates the check digit used to detect errors. If even one measurement falls outside the allowed tolerance, the scanner simply rejects the entire scan. That's why, every now and then, you hear nothing at all instead of the familiar beep. After all those calculations, the scanner finally produces a result. But the result still isn't the product. It's only a numerical identifier. Think of it like a license plate on a car or a passport number assigned to a person. By itself, that number contains almost no useful information. It's simply a unique key pointing somewhere else. For the first time in this entire journey, information leaves the scanner. That identifier is sent to the retail point of sale terminal, where a database searches for a matching record. Within milliseconds, the computer retrieves the product name, its current price, inventory status, taxes, discounts, and every other detail displayed on the checkout screen. This also reveals one of the biggest misconceptions about barcodes. The barcode never stored the product name. It never stored the price. It never stored promotional offers or inventory levels. It only carried a unique identifier. Every piece of information you see at the checkout counter already existed inside the store's database long before the scanner ever saw the product. Now, let's watch the entire machine come to life one last time. The red laser diode module generates a perfectly stable beam. The high-speed scan mirror assembly sweeps it across the barcode. Reflected photons reach the photodiode sensor module. The signal processing PCB amplifies, filters, and digitizes the signal. The barcode decoder processor reconstructs the code. The retail point of sale terminal finds the matching record. Then, beep. The exact same sound we heard at the beginning of this video. But now, it means something completely different. It isn't just confirmation that a product was scanned. It's the final step in a chain of optical physics, precision mechanics, analog electronics, digital signal processing, and computer databases, all working together in less time than it takes you to blink. The most fascinating part isn't that a barcode scanner is intelligent. It's that no single component inside it understands the product at all. The laser only creates light. The mirrors only redirect it. The photodiode only counts photons. The electronics only process signals. The decoder only reconstructs patterns. Yet when every component performs one simple task with absolute precision, the entire machine achieves something extraordinary. That's how engineering transforms light into information, and a single beep into one of the fastest transactions in modern civilization.